In this video, we will revisit the concept of enthalpy and discuss how we can determine the enthalpy for a reaction using various mathematical tricks by applying what we will call Hess's law. So we had previously mentioned that enthalpy is essentially the heat that is transferred when we are working under constant pressure conditions. So enthalpy is defined as the amount of heat exchanged under constant pressure conditions, such as those in a beaker. The enthalpy of a reaction is the amount of thermal energy either given off or absorbed by the reaction or process, making it something that we will be very interested in for chemical processes, particularly if we're trying to use like a fuel or something where we're trying to get energy out or put energy in to a system. Now, one thing that we're going to keep coming back to in our discussion of enthalpy is that enthalpy is a state function. And again, a state function is a property whose value only depends on the initial and final conditions, not on the path that you take. We will use this with Hess's law, which takes advantage of the state function property to come up with alternate ways of determining the difference in energy between a starting point and ending point, particularly for reactions that would be difficult to do in the lab. Now, the concept of enthalpy can be applied to a wide variety of processes. However, they are all related to each other in that we are looking at the difference between a starting point and an ending point. Using the IUPAC nomenclature, that's the International Union of Pure and Applied Chemistry, it is recommended that the way that we will use our shorthand notation to describe enthalpy for a particular process is to start with a delta, and then here you have your label for the type of process followed by H. So for example, a transition, a phase transition, such as going from a solid to a liquid like fusion, you would have the delta followed by the indicator for that particular transition. So you would have delta FUS Now, while this is what is recommended by IUPAC, a much more common usage is delta H followed by the indicator. So instead of for like fusion having delta FUS you would have delta H subscript FUS. This is the one that I will be using because it is much more consistent with what you will see in literature and the vast majority of text. So while the more correct fashion of doing it would be using IUPAC's recommendation, we will be using the more common representation of delta H followed by the subscript indicating what type of process you're looking at. And there are a wide variety of processes that we would be interested in knowing the amount of thermal energy that's required to do that particular process. So like sublimation, going from a solid to a gas, or deposition, which would be going the reverse, although it would still be called the sublimation. The value that would be listed would still be the sublimation. As we will see later, if you're going in the reverse direction, you just put a negative sign in front of the number, and that's how you treat it. Okay, so we can combine some of these to look at more complex reactions. So for example, if we know the value for the enthalpy of fusion going from solid to liquid and the enthalpy for vaporization, liquid to gas, because we are only interested in our starting and ending point, we can actually add those two values together, in essence going solid to liquid, liquid to gas, to figure out what it would be going straight from solid to gas, right? If your path goes solid, liquid, liquid, gas, it's the same in terms of total energy as going solid to gas, and that's because enthalpy is a state function. It only matters where you start and where you stop at the very end, right? So if we go solid, liquid, liquid, gas, our starting point is solid, our ending point is gas. That's the same as sublimation going from solid to gas. So we can use that sort of process in what is called Hess's law. So for Hess's law, because enthalpy is a state function, it is possible to determine the enthalpy of a reaction or process by summing other enthalpies of other reactions if they are at the same temperature and if the reactants and products sum together to cancel out, yielding essentially the desired reaction. So if you're trying to model a particular reaction that might be difficult to do in lab or do under controlled fashion, and you have two reactions that have a common intermediate, you can go from one reaction, the start of one reaction, to the end of the other reaction, going through that common intermediate. That is essentially one of the tricks that we'll be using with Hess's law with an example that we'll be looking at. So if you change the direction of a reaction, you change the sign of the enthalpy of reaction, because the enthalpy of reaction is the difference between your starting point and ending point. So if you change the direction of the reaction and make your products your starting point and your reactants your ending point, then the change in energy would be going in the reverse direction, and so it would be the negative of the process that you would find in a table. If you need to multiply the reaction to get the molecules to cancel out, then you will multiply the delta H reaction by the same value. We will now use Hess's law to determine the enthalpy of a reaction for one that would be difficult to do in a laboratory setting. So let's say we're interested in figuring out the enthalpy of a reaction for this particular reaction. But we don't actually have the ability to do this one in the lab, or we haven't yet done it in the lab, and so we're trying to figure out how much energy we need to take into account for our setup to make sure that we've cooled the system down or we are supplying the correct amount of heat to get the reaction to go. Okay, so we have three different reactions that we've found that we think we can add together to come up with our overall reaction. Now, when you're doing problems like this, the way that you want to approach them is look in your reactions that you're trying to sum together to get your overall reaction for components that you can identify with being part of your overall reaction. So here we have, like in reaction 2, we got the N2O5. This is the only location in the three reactions where that is at, and we have N2O5 here as a product. Similarly, we have our nitrogen in reaction 1. There's no nitrogen anywhere else. We have oxygen here in reaction 1, but we also have oxygen here in reaction 3. So what I would do is try to set it up such that we use reaction 1 to account for our nitrogen. We're going to use reaction 2 to account for our dinitrogen pentoxide, and then we'll see what we can do with reaction 3, whether we need it or not. Okay, so if we look at where things are located, I can use reaction 1 as it's written in this order. But in my balanced chemical equation, I have two nitrogen here, and in the equation here, there's only one of them. And so what I'm going to need to do is take my first reaction and run it twice, right, to get all the nitrogen that I need. So I'm going to take this and multiply it by 2 to account for the number of nitrogen that I need. Similarly, for reaction 2, first, the N2O5 is a reactant in reaction 2, but I need it to be a product. So what I'm going to do is I'm going to flip this reaction, flip my reaction, and in my overall reaction, I need 2 of them. But in reaction 2, there's only 1, and so I'm going to need to run this one also twice. So I'm going to flip it and run it twice. We'll see where we're at with reaction 3 once we add our stuff together and see how it's coming together. So writing out reaction 1, doubled and in the direction that it's at, this would be 2N2 as a gas plus 6O2 as a gas plus 2H2 goes to give 4HNO3 aqueous. Reaction 2, we're going to flip it, and so the HNO3, the nitric acid, goes on the left-hand side. We need twice as many, so it's 2 times 2 is 4 HNO3 aqueous. That's good because that will allow us to cancel out the nitric acid from reaction 1. This goes to give 2 N2O5 plus 2 H2O. N2O5 as a gas, H2O as a gas. Okay, so if we look to see how things cancel out, we have 4 HNO3s on the left here, 4 on the right. Those will cancel out when we add. Nothing else so far cancels out. So if we compare the reaction that we're after with where we're currently at, we have the correct number of nitrogen when we add them together. We have the correct number of N2O5, but we have extra water, which we don't want. We have hydrogen, which we don't want, and we got too many oxygen, right? And so we're going to use reaction number 3 to get rid of a bunch of that stuff. If you look at reaction number 3, water is as a product, and so we can use this to get rid of our water that we get from the flipped reaction 2. So I'm going to use my reaction number 3. I'm going to flip it. Okay, and this will get rid of the 2 waters. So I'm going to flip it, but use it as it is. So this would be 2 H2O as a gas goes to 2 H2 as a gas, and up here this hydrogen should be as a gas, plus O2 as a gas. Okay, now if I look how things are going to play out, these 2 hydrogen here cancel out the 2 hydrogen here, these 2 waters cancel out those 2 waters, and this oxygen is going to cancel out one of those, giving me 5 oxygen left. And so if I look at the components that I have from my 3 reactions that I'm about to add together, you can see that they will sum up to be my overall equation. So if I add everything together that's left, I get 2N2 as a gas plus 5O2 as a gas goes to give 2N2O5 as a gas. Okay, when we're trying to figure out the energy values listed here are per mole of reaction as it's written. So in our use of the first reaction, we doubled how many times the reaction is run. And so the energy for this particular step needs to be twice as much here as it was listed in our table, right? We're essentially using the reaction twice. Each time the reaction is run, it's exothermic because energy is coming off, and it gives off 207.4 kilojoules per mole of energy. So what we're going to do is we will add all of our values together to come up with our overall change in enthalpy of reaction. So we can just add up our values, taking into account what we have done here. If we flip the reaction, we flip the sign. If we double the reaction, we double the value. So our overall delta H reaction would be equal to 2 times the value from our first one, as written, 207.4 kilojoules per mole, plus the value from our second reaction. Now we flipped it, so we will switch the sign. We doubled it, and so we'll multiply it by 2 times the value, which is 218 kilojoules per mole. And then we're going to add the value from our third reaction. We flipped it, so it gets a negative sign, but we used only one of them. We didn't double it, so the number will stay as it was. We are not going to double or triple or doing anything like that. So this would be negative 285 kilojoules per mole. So if you plug this into your calculator, what you'll get is the delta H reaction will be negative 565.8 kilojoules per mole of the reaction that we have written up top. Or you could also think about it as this reaction. They are the same reaction. So yeah. So that is our answer. That is the amount of energy that will be coming off of our reaction. So if we are planning on doing this one in the lab, what this tells us is that it's exothermic. And so we'll need to, in our experimental preparation, be ready to handle the heat that is given off by this reaction. Okay, now the last thing is sort of what we were doing before. We can combine the enthalpies, because it is a state function, to do reactions that are normally very difficult to do. We had previously talked about how the enthalpy for transitions, we can add them together. So we could take the enthalpy of our fusion going from a solid to a liquid, plus the enthalpy of vaporization going from a liquid to a gas, to come up with our value for the enthalpy of sublimation, which is from solid all the way up to gas. And that's because, again, enthalpy is a state function. It only matters where you start with and where you end. So we could add our two reactions together of solid to liquid, liquid to gas, and that would give us the same value as the one that we want, which is solid to gas. Another one that we use this for commonly is the Born-Haber cycle, which is used to determine the lattice energy, or the amount of energy that you get from forming a crystal for an ionic compound. Now, the lattice energy itself is actually very difficult to do experimentally, right? And that's because it's defined as taking your ions in the gas phase, reacting them together to get your solid. Now, the ions in the gas phase, first, they are very difficult to get things to be ions in the gas phase, let alone having them in the same container to react together, right? But what we can do is add all of our energies together. We could keep our containers separate as long as we can map out a complete cycle, leaving out a particular component. We can come up with what the energy of that component is. So the difference between the potassium chloride as a solid and our system in this particular arrangement, where the potassium is a ionized gas that has given up an electron, to the arrangement where the potassium is as an ionized gas plus chlorine as, a monatomic chlorine atoms, right? We can actually do this in the lab. And so the difference in energy between potassium chloride solid and that is the same whether we are going through a bunch of different steps, or if we're using the lattice energy and then talking about the amount of energy that we get back from taking an electron that came off of the potassium and putting it onto the chlorine atom, right? So the way that experimentally we find the lattice energy is by looking at the amount of energy that we get by reacting the potassium metal as a solid with chlorine gas. That would be this energy here, right? The difference in energy here. We do that in a separate experiment, write down that energy. And then in an additional set of experiments, we keep the potassium separate from the chlorine. We can then melt and then turn into a gas or sublimate the potassium solid to get potassium gas. The chlorine at this point hasn't changed. It is in a separate container. We can then take the diatomic chlorine, break it apart into individual atoms, chlorine atoms, and that amount of energy in this case is 122 kilojoules per mole. Okay, we can then put in a good amount of energy, pull an electron off of the potassium so that we get the potassium ion, that electron, and the chlorine atom. Then we take the electron, put it into the chlorine atom, and we get the potassium ion in the gas phase, chlorine ion in the gas phase, and we know the amount of energy that it takes to go all the way up and then down to this point. To complete a cycle, if our enthalpy is a state function, which it is, if we start out at a particular place and end up at the same place, then the initial and final values, right? The initial and final conditions are the same, and so the change in enthalpy should be 0. So we know the enthalpy that it takes to get to this location, and so we can subtract, or we can from that figure out what we are missing, the amount that we are missing here in terms of energy of our potassium in the potassium ions in the gas phase, our chlorine ions in the gas phase, versus the energy that we have of potassium chloride as a solid. That difference in energy between the two paths, going sort of up and then down to here, versus this one-step path, figuring out that difference allows us to know the amount of energy for forming the ionic solid from the ions in their gas phase, which is known as the lattice energy. The lattice energy itself would be very, very difficult to do experimentally, but it is a useful number to know because it gives us an idea of how stable the crystal structure is that we're working with. So this is a way that we can do reactions, or we can calculate the amount of energy that a reaction would take or give off for processes that we can't actually do easily in the lab. We use sort of this cyclic path, and then the difference between our path where we end up with and where we start would be the energy of the particular step that we're going to have difficulty doing in lab.